This is big point here, very specific to aqueous solutions, so in water. Okay, so an acid is something that produces H plus ions in aqueous solution, which, by the way, H plus, you could write it that way in a chemical equation. However, in reality, it exists. It's too active to exist on its own, the proton. So what it does is it binds to an adjacent H2O, and it forms H3O plus, which is called a hydronium ion. Okay. So in reality, they don't exist as H plus, but you can, yes, you could write it out that way, and you already know this because you've seen it many, many times with this. HCl plus, if I just say HCl, and then I put water on top here, what do I get? H plus Cl minus. That's what I'm saying. So you see it like that. However, if I write it out like this, what it really is H3O plus Cl minus. And this is how it actually exists. Those are the only variations of what I just said. Okay? But this is acceptable, just as long as you understand. And a base in water produces the OH minus ions. I gave you the first example with the KOH, the obvious one, but that's why ammonia is considered a base, because ammonia with water forms the OH minus. The idea of it just forming an OH minus, it doesn't have to come off it itself. Those are the simple definitions from Arrhenius. So here you go, there you are, thing I just wrote on the board. All you have is you put the HCl as a compound in as a solid, and it separates into these ions. These H pluses here are actually H3O plus pluses, which are hydronium ions, and these here being in the solution is what makes it an acid. It's a strong acid because it's an arrow that goes all the way here, which means all the H2Os compete away the H from the Cl. There are no HCl compounds left. They're all like this. That makes it a strong acid.
How is it strong electrolyte?
Yeah, a strong acid is a strong electrolyte.
Right.
Anything that has the ions in it. So anything that separates completely, that's a strong electrolyte. This is specifically a strong acid, is it because they have their own properties. So sodium chloride would also be a strong electrolyte, but it's not an acid.
Right.
That's why we're making the distinction of an acid here, yes, but it's also a strong electrolyte. And as I just got done saying over here, good thing I know this, look at it, H plus with this, when it's in the solution, will bind to it and you'll form this, and this is called a hydronium ion. I wonder why they don't, do they state that somewhere? That's a hydronium ion, you should know that term. No big deal, nice and light, hopefully. Okay, good. Now base, as I put on it, we already did this with KOH. KOH breaks up into K plus and OH minus. This time it breaks up into Na plus and OH minus since it's sodium hydroxide. And because it separates completely, it's a strong base. And you see all the Na pluses here. But more importantly, as a strong base, you see all the OH minuses. And that's what makes it basic. Right? And of course, an H plus plus an OH minus forms H2O. As we know, that is called the classic acid-base neutralization reaction. And there's this neutralizing. Neutralization means that it changes it from an acid to a base or a base to an acid, depending on what you're neutralizing. Okay, good. Second definition, Brotstedt-Lowry. Once again, this one is something I might have introduced to you at some level up to this point, because this is also a very common one. This expands the definitions a little bit more, because the definition, the first definition, the main component of that was that it was in water, right? So what if I have something not in water? Okay, that's where this expands a little bit. So the Brotstedt-Lowry definition focuses on the transfer of H plus ions in an acid-base reaction. Not necessarily in water. All I need to do is have an H plus or a proton go somewhere or be grabbed by something. Okay? So if it takes it up, it's a base. If it gives it off, it's an acid. Doesn't matter if it's in water or not. That's the expansion of what Brotstedt-Lowry came. And my understanding is I think they came up with these around the same time. One guy was in Sweden. These guys, I think, at least one of them was in England, I think. Maybe both, I don't know. But it was around the same time they came up with both their definitions, just so you know, historically. So H plus is a proton, so this is just a proton donor or acceptor. So an acid is a proton donor, and a base is a proton acceptor, according to Brodsted-Lowry's definition of an acid base. That's the only variation. It does not have to be in water now for that to happen. Okay.
Liquid solution, that one just talking.
So, how is this different? Same thing. All right. So, looking here. Okay. So now the key here is, where before in the Arrhenius, what we did was obviously we looked at it, we put it in water, and we saw what the chemical equation was based on our, our Chem 65 knowledge, basically, right? So here, I'm going to say, okay, let's look at the equation and let's determine which one is the acid base. By the way, Brodsted-Lowry definition does fit with something in water. It just doesn't have to be in water. I want to make that clear too, right? So it's a more broad definition. So here I have HCl, H2O, H3O plus, and Cl minus. You already know the answer to this, so don't think about it in terms of what you know. Here's how you figure out something that would be more challenging. I have this here, and I have this here. When I look at this here, and then I see what happens to it over here, what did it do? It gave away a proton. That makes it an acid. This here was here to here. What did it do?
Gain the proton.
It accepted, so this is the base. So when you're looking and deciding which one is an acid or base from a balanced chemical equation, you're only deciding that from the reactant side. It sounds really easy what I'm saying. When I don't say this, and I've said this maybe at a lower level, whatever, they start assigning these things as acids and bases. Those are not the acids and bases. It's what you start with. But when I now look over here, I say this is the Brodsted-Lowry acid. It became this. It is now the conjugate base. Conjugate meaning just whatever it came from and what is left of it. The original acid becomes the conjugate base. The original base becomes the conjugate acid. That's the acid-base pairing of Brodsted-Lowry. That's it. Is that okay? But this is always the acid base, this is always the conjugate side. You can't have the opposite. And of course, unless you're dealing with an arrow. And by the way, the reason is if I looked at just this, if anything did go the other way, this is acting now as what? This is picking up the H going this way, hence the conjugate base. So you can look at it from that perspective as well, but you just gotta know your conjugate.
So if this definition agrees with the Arrhenius definition and it's more universal, why do we use the Arrhenius? Or the Arrhenius definition?
There are some slight differences that you come across in both. I haven't pointed those differences out, but you can. And so this way you can, either way you can use, and it also depends on what that's for. You notice in the Arrhenius, you don't use the conjugates. There's no conjugate system. In this case, this is also just in water.
Yeah.
You're gonna see some other system. Wait till we get through this, and then you might want to re-ask me that, and maybe I'll point out some things at that point. But you're gonna see quite clearly where some of these things are gonna vary. Oh, they didn't do the conjugate? They must some point, okay. Maybe I jumped too soon. So here, I look here, and by the way, just to, as I'm seeing this now, just to kind of gauge what you were saying. If I looked at this as Arrhenius is acid or base, what am I saying here?
That the NH3
The NH3 is what?
is the base,
Is the base.
right?
Okay. Now, when I look at it from Brodsted-Lowry, what am I saying about this?
I guess we're making H, you're making water into acid.
This is acting as what? This becomes this, so what happened to it?
It's gaining
Accepted, so this was a base?
Right.
What is this?
acid.
An acid. This would not have been defined necessarily as an acid in, so this is, I'm coming across this, I'm seeing it right now. But there's a lot more that you'll see that will help out that. So obviously we've just defined this as a base and that's an acid
Right.
in Brosted-Lowry definition. So what is this?
The conjugate.
Conjugate acid, and this is?
Conjugate base.
Absolutely, that's it. No big deal, right? Did we do this in 101?
No.
I don't think so, right?
Not this.
No, okay, good.
At least not the
Did I do it in
definitions.
65? Can't remember, I think we do this in 51, is that what you're
I
talking
think
about?
it's 50, just 51.
Is it 51 because it's more biological based, because these things happen in a biological system, so it's, okay. Yeah, I think you're right. We don't go into the same detail, but yes, I think we do. Okay, so then, let's see. So, by the way, so some things can be amphoteric, which mean they could act as both an acid and a base.
Like water.
And that's here, like water, can accept the H and become a hydronium ion, or get rid of the H and become a hydroxide. Just means it depends, right? Why does it depend? Because it depends on what it's competing against.
Right.
The same thing I mentioned earlier, which is why I brought that up, to make that more smooth when I use that terminology from here on out. So here, what's happening? Is this my acid or base? What happens to it?
Oh, that's gonna be your answer.
This is my acid,
Right.
because it gives off the proton, and that makes this my conjugate base. And this is my base, and this is the conjugate acid, absolutely. This is no big deal, so I'm gonna start, whoops. Oh, here's another one. Okay, so in this case, what is this? This goes from here to here. This is the
Base.
base, and this is the conjugate.
Acid.
And this is now what? The acid. It gave up the hydrogen, and now it's the conjugate base. So all they're doing is showing here that the H2O can be a base or an acid, depending on what's in it and what it's competing against. Are we gonna be able to figure out like how that works in terms of like if I had concentrations and stuff?
Huh?
Yes, ice charts, equilibriums. When these things form equilibriums, I can figure stuff out.
Right.
When they're all going one way, it doesn't matter. That means these are, by the way, this, I should point, I just recognized. This is a strong acid, so this is what happens. This is actually a weak base, so there is a double arrow. This is literally an equilibrium that was just modified to make it look like it's not. I haven't brought up the idea of strengths really yet, but if it's a strong acid and
All the
base,
way.
then it goes all one way. If it's a
Right.
weak acid or base,
Back
then
to
it has
base.
the equilibrium. And then from this one, you'd be able to figure out exactly what amounts you have at that equilibrium in probably a couple weeks to get to that. Okay, let's try. All of a sudden, it's not so simple. You love how that quick transition, but it doesn't matter. Is this the acid or the base, and is this the acid or the base? Can you quickly identify it in this particular system?
Yes.
Yes. Yes, why?
The H being donated, so this is
This
the,
one?
That's the acid.
Versus this.
That's the base.
What are these doing here? Are those part of the acids?
No.
No, why?
Is the O?
Connected to carbon. Remember you saw that carbon structure?
Right.
That's why they're embedded, but anything in the front or the end there, you see, this is put specifically because it's connected to the oxygen as an oxyacid.
Right.
So that one's coming off, there's no oxyacid here, and there are different numbers, 6 and 5, just to follow them per side.
Right.
To make sure that, so here, this is gonna give up the hydrogen because this is gonna become this.
Right.
This is gonna accept the hydrogen because it's gonna become this. So this is the
Acid.
acids, this is the base, this is the conjugate base off of the acid.
Mhm.
That's the conjugate acid-base pair. This is the base and the conjugate acid from the acid-base pair.
Right.
Okay. Just make sure you're defining acid-base from the left side and the conjugate on the right side. And you're comparing from one side to the other to determine where the hydrogen went.
Mhm.
Okay. Should say hydrogen ion, I really should be saying proton. But, I think you guys get the point. And if you don't, just ask, and I'll clarify. And the reason is because the hydrogen would have that electron. Okay, what about here?
Okay.
What's the acid, what's the base?
Base is the water.
Base is the water, or base is
sorry,
the acid?
sorry, the acid.
Or the water is the acid?
Uh-huh. See how
This is the base, so this is
Yeah.
the conjugate acid of the base, this is the base, or this is the acid, and this is its conjugate base.
Right.
Okay, no big deal. Oops, make sure we're clear on that. Acid, base. Okay, here are the conjugates, so since I've already described this, I can move through this. Oh, you notice how this time it has a double arrow there for that same equation?
Yeah.
You pick and choose how to use things. Since we haven't actually described the strengths yet, I can still do that. As soon as if you saw this after I described the strengths, you'd tell me right away that other one. That doesn't make sense. All right, so here I have an equilibrium all of a sudden, right? But we're looking at the conjugate acid base. This is going to be the base. It's going to accept the hydrogen. That's going to make this the acid. This becomes this, so this is the conjugate acid, and then this becomes the conjugate base. that makes this easier since I started that right away. I think it's odd to kind of separate it. It makes it seem like they're not all the same. Yeah. So hopefully this is easy. Let's do a couple more before we get out of here. Conjugate acid is any base in which a proton has been added. Right, no big deal. This goes to here. Same, nothing special here. And you remove the H plus, this is the conjugate base. And just in case you weren't clear on anything I did, you can look at these slides. The most part is everything I've already said. So let's do it here. Which one's the acid, which one's the base? This is the acid, it gives up the hydrogen. That's its conjugate base. This is the base, that's its conjugate acid. Right? Everybody agree? Okay. At this level, I think that's too easy. Here and here. So this is now the what? The base. And this is its conjugate acid. This is the acid, and that's its conjugate base. And you got more? Oh, good. Which pair is not a conjugate acid-base pair? This is good because this is the kind of question I give you all of those, and then on the exam I ask you something that seems different even though it's the same exact concept.
Okay, so
Right?
B is
So
not.
what's the answer here?
B is not,
B, why?
because it doesn't
It's not
have the.
donating or gaining.
Exactly. You have the same number of hydrogens that are the acid hydrogens on both.
Right.
Here I have hydrogen, so this would be the acid. This would be its conjugate base. By the way, on an exam, if I asked about an acid conjugate base, you would have to make sure you do it in the right order, right?
Right.
I could have said here, you know, base conjugate acid. That would make this wrong because the first thing is the first, this is the second. Here, this would be what? The base, and this would be its conjugate acid. So how, you know, what their sequence is important, make sure you pay attention to that. This can't be either because I don't lose or gain a hydrogen here. I've changed an oxygen. That has nothing to do with it. Right? Just to make that clear. But it's a great question because some of you got it right away, which I would expect if you understood the concept. Some of you actually understood the concept and might have actually paused and weren't sure. And that's what what most of my tests are, right? They're designed to see some of it's regurgitation. So, you know, are we at least passing the class? Some of it is then, can you take it and do small manipulations to it? And maybe that's just passing the class to a B. And some of them are going to be more challenging where you have to manipulate it using all the concepts you know, but nothing outside of what you know. So you have to look at these not linear. Look at them as what they mean. Take a step back in the question and say, what is it asking for? What do I know? Now, how can I solve for it? And that's the difference between a B and an A, in all fairness, in these classes, just to keep that in context before we have our first exam.
You said what can you not do to C? When you said the example, like it has to be in order.
Oh, if I said this was an acid conjugate base pair, that would be right. If I said this was a base conjugate acid, this would be wrong.
Okay, yeah.
Based on the order they were in, but this one would be right. That's a base and its conjugate acid. So the order would match whatever the order is given here.
Okay.
Most of you would actually get that, but one or two might get caught up in that, and those are the kinds of things that you understood the concept, you just didn't pay attention. And so I'm trying to make sure I can catch everybody that might not pay attention to something like that. Okay, that leaves our third definition, so we can close out this this lecture, and we're not picking this up again, but I wanted to cover all three, where this is the Lewis definition, and this broadens even more what can be an acid or base. So obviously everything we said before can still be an acid or base, but now this is a little bit more. And what this is really saying is that anything, so you're going to have a couple things here, and you see you have these two dots here. These are the electrons, right?
Right.
It's a lone pair. When you have those, and they could pull something in, it's considered a base. Doesn't matter what it pulls in anymore. And anything that goes to it is an acid. So essentially that's this, right? In something that actually does produce the hydroxide, that's already obvious.
Right.
This is the base with the lone pair, and this is the acid because it's taking the lone pair. Now it's expanded. It doesn't have to be a proton. And therefore, a Lewis acid or base is now defined as giving up or taking in based on whether or not you have a lone pair to do that. So it's an electron deficient thing is going to be an acid. Electron abundant thing will be a base. Okay. So call it electron pair acceptor is the acid. It accepts the electron pair, and the electron pair donor is the base, as opposed to just a proton transfer. Different definition. So this one is the base, this one is the acid. But what if I had something here that wasn't an H+?
Same thing.
It would still be an acid.
Yeah.
Yes, that's the difference, absolutely. Okay, that's the third definition. And of course, that's much more broad because once again, I don't now need it to be a hydrogen or a proton. Okay. This just overlaps the definition of Brotstedt-Lowry to initiate it. But it's going to be, let's take a quick look. Everything I already said, so let's take a look at this. What about that? In Lewis's definition, what is this and what is that? This is the acid, that's the base, right?
Right.
Why is this relevant here? Why BF3? What is BF3?
Oh, the structural.
Do I know how to make structure? How do I make a structure? Let me make sure that
The center ion.
we figure out the Lewis structure,
Yeah.
right? And we do that by the total number of valence electrons. How many valence electrons in B?
3.
And what else is there? F, how many in each F? For a total of?
No.
24. What's the center atom?
B.
And F, F, F,
That's it.
2, 4, 6. Minus 6 leaves me with 18. 2, 4, 6. 2, 4, 6. 2, 4, 6. Minus 18. In a traditional Lewis structure, that would not work because that's not an octet. However, it doesn't want to be an octet. Right? This is an exception.
Yeah.
It's exception because it's on, what
No.
level is it? Is it on? What period?
Period
2.
Yeah.
So what orbitals does it have? Just a P, no D.
Right.
Doesn't have any Ds, and it likes to, it's an exception to the rule. Did I talk about this exception in 101?
Yes.
Okay, good. So then, therefore, it doesn't have anything here. I mix that with this one, binds right to there. And that's what I'm seeing here. This becomes my acid, that's my base. Even though this isn't a proton. Expanded that definition. Okay, with that, let me let you go, so you can go eat. And we'll pick this up on Thursday, a week from today. I'll see you Tuesday for the exam, and you guys should be fine if you study. If you have questions, feel free to email me anytime.